Hey, complex variables people. We're about to get beyond the algebra of complex numbers. And what we're going to talk about today are functions, and in particular, complex valued functions. Just to set the stage for what we're about to do, let's consider the definition of a real valued function from a set x to a set y, where x and y are subsets of the real numbers. A real valued function f from set x to set y is a rule that assigns to each x value in the set x exactly one y value in the set y. And we're usually very, very adamant about the fact that a function assigns to each x value exactly one y value, no more, no less. And just for the sake of example, let's consider the function that maps the non-negative real numbers into the real numbers. For the sake of example, let's consider the function square root of x. F evaluated at 9 is the square root of 9, and 9 has two square roots, positive 3 and negative 3. Each of these is a square root of 9. But since the square root function is a function, it can only return one value for each value that we plug into the function. So, by convention, we've decided that the real valued function, square root of x, returns only the positive root. And that's worth noting. So it returns only the positive, or in the case of x equals 0, the non-negative root. And that's all that it can do, because it is a function, and a function only returns one real value for every real value that we plug in. And that's caused some concern among people who will look at something like this and say, but suppose we want the negative root. Well, there's a solution. If we want the negative root, we do this. We stipulate that we want the negative root and that we get negative 3. And this is something that we're somewhat familiar with, probably more familiar with than we realize. One thing that gives evidence to the fact that we are familiar with this convention of the square root function only returning the positive root, and that if we really want the negative root instead, we put a negative sign in front of the square root sign. One evidence of the fact that we're really more familiar with this convention than we might realize is the formula for the solution to a quadratic equation. The quadratic formula, typically a quadratic equation has two roots, unless it has a double root. But we have negative b plus or minus the square root of, let me see now, don't tell me, I'll get it, b squared minus 4ac all over 2a. This formula will give us both roots of a quadratic equation. And to get one root, we'll take the positive square root. To get the other root, we'll take the negative square root. But we only do one at a time. And this square root, because it's the square root function, only gives us the positive root. If we want the negative root, we have to have a negative sign in front of it, like that. So we are familiar with the convention of a real valued function only giving us a positive or non-negative root. And with real valued functions, that doesn't cause us too much concern. But the issues arise with complex functions. And apparently with complex functions, it's not as easy to sweep all of this under the carpet. So let's set the stage for what we're about to do with complex functions by continuing to work with the square root function. But we'll say now that this is a complex valued function. Let's say that f is now a complex valued function. It maps the complex numbers to the complex numbers. And it's defined by f of z equals square root of z. Well, we still got the same problem here. We're going to have two roots. And we kind of like to acknowledge all of the roots. Well, why? Well, remember on our test, which all of us did quite nicely on, by the way, maybe we had the 8th roots of unity, I'm not sure, but I'll do the 4th roots of unity. The 4th roots of 1. Well, there are 4 of them. And they are 1, I, -1, -I. And maybe I listed them in that order because if we plot these roots on the unit circle, we can start with 1 and then going counterclockwise, we have I. And continuing to go counterclockwise, we have -1. And then going counterclockwise again, we have -I. The 4 roots of unity. And we don't really want to ignore any of the roots. I think even now, we'll still look at this one and say, well, you know, this is the main solution. The 4th root of 1 is 1. Well, yeah, these other guys, these are 4th roots also, but this thing is the main solution. Just like The square root of 9, well, this is the main solution. And yeah, there's also -3, that's a root also. But, you know, we only take the positive root. Well, situations may arise where we want to acknowledge all of the roots of an equation. And so here's what we do in the case of the square root function, or z to the 1/2. We say that this is a principal root, and this other guy is a root also. And 1, if we're taking the fourth root of 1, 1 is a principal root. And these other guys are roots also, not the principal root, but they are roots nonetheless. And so we sort of have to redefine a function so that it's still a function, but at the same time it doesn't ignore any roots or solutions. And so for the square root function, yep, watch me fumble around here. If z is not just a complex number, but also a real number, so let's say that z is a non-negative root. But we'll say the positive root of z is the principal root. Well, okay. But now what if z is a real number, but it's negative? If z is negative, then negative z is positive. And so this will be principal root of z, rather negative z, principal root of negative z times I. So for example, square root of negative 9 is equal to negative, square root of negative 9I, or 3I. Principal root. What would the other root of negative 9, square root of negative 9 be in this case? It would be the root of 9 that doesn't happen to be the principal root. So I guess that would be the other root, square root of negative 9 equals negative square root of negative 9I, or a negative 3I, the other root. So, defining the complex function f of z equals square root of z, or z to the 1/2, we can say that f of z has two branches. Each one of these branches we would consider to be a function in its own right, in the sense that it will return exactly one value for each value that we plug in. You know what? That's such a good observation. I don't think I should go on without drawing attention to that. Each branch is a function in its own right. And returns exactly one value. Each branch is actually a function in the conventional sense, where we plug in one value and exactly one value comes out. So the complex function f of z is actually made up of two branches, each of which is a function in its own right. The principal branch, and this is a term that we will use for such functions, the principal branch yields the principal root. So the principal branch of the function, when we plug in 9, will give us 3, the positive root. The principal branch, when we plug in negative 9, will give us the principal root, 3 times I. This other branch, and we don't really have a name for it, this other branch yields a root other than the principal root. We plug in 9, it doesn't give us the positive root, it gives us the negative root. We plug in -9, it doesn't give us the principal root, it gives us the other root. And the reason I'm saying this right now is because a lot of complex functions will not be functions in the conventional sense, where we plug in one number and out comes exactly one number. A lot of complex functions return several values for each value that we plug in. And so what we do is we take such a complex function and we assign it a principal branch, which is a rule that says this principal branch yields exactly one value for each value that we plug into the function. And this value is going to be our principal root, our empirical root. Empirical is not a good name. Principal root. There is a better word for this, and since I have a vocabulary consisting of about 6 words, I can't think of it. But it'll have a principal branch and one or more other branches as well. Thank you. The word I was looking for was canonical. So this principal branch we can think of as being the canonical branch, the one that yields the principal root. And the function may yield other values as well. The function may have other branches that yield values other than the principal root. But the principal branch will yield the principal root, and we would say that this principal branch defines the function in the canonical sense. For example, the square root of a positive real number is going to be the positive root. That's the square root function in the canonical sense, and that root is the principal branch. Now we'll look at some other functions.